So let's talk more about this. So we said the goal is to adjust the, if we cannot just adjust gain k and move along the root locus and get what we need, now we have to reshape the root locus by adding poles and zeros. But the first question might be, well, what is exactly adding a zero or a pole does to the root locus? So let's first look at that. So what happens when we add a pole to the root locus? So if you look at here, the let's see if I can make this bigger. Hopefully I can. How about this? Oh no. There we go. So here on the left top picture in part A, you see that here I have a root locus of a system with one pole only, and then I have added one more pole to the left of that, and what happens? The system that could only have poles on what? On the real axis, so the behavior was completely what? Yes, that was overdamped. Now, if I add one more pole, the root locus is now quite vertical. It has these two portions, small ones as well. So after a little bit of real roots, now I'm kicking into what? Imaginary roots. And these imaginary roots have a negative real part. So what kind of behavior is this? Yes, that is underdamped, right? So unless the roots are on these small portions, the rest of it is underdamped behavior. And if I add one more pole, now what happens? Again, for these areas, the system, at least for those poles, the system shows overdamp, but for these two poles that are now moving on these two branches, what happens? Again, underdamp, but with one difference with respect to B. Now, you see, if I move K to some large number, what happens? My root locus moves to the right-hand side of the imaginary axis, so the system becomes unstable. So here in parts A and B, regardless of how much you change K from 0 to infinity, you always have the system stable, right? Because there is no dominant ever on the right-hand side. But here, now you do. So it seems like from the kind of stablest type of system, most stable type of system, that is this one, now I'm making it a little more oscillatory, and now here not only oscillatory, at this point the oscillation can grow instead of being damped. So adding a pole to the system, first of all, will shift the root locus from the left side to the right side, and it can then have what? The effect of instability. So yes, when we add a pole is similar to what? Yes, it is similar to adding an integrator to the system, and integrators, although they remove steady state errors or help improving it, but will make the system slower and less stable. Now you might wonder why this is happening. Why is it that the poles are moving to the right side? Why is it that the root locus is just bending to the right and shifting to the right? What do you think? What is your idea? So I'll refer you back to this formula here. Maybe this one can give you a hint. This guy here, the angle of the asymptotes, if you look at the angle of the asymptotes, what is it? So the important thing is here, this denominator. Let's see. Can I still write? Yes. So this denominator is the big guy here. What is it? It's n minus m, number of poles minus 0. So if we add more poles, means we are making n bigger. And when we are making n bigger, we are making the whole denominator bigger, right? In other words, what happens to the angles? Yeah, the angles are going down because you are dividing 180 by a bigger number. So in this case, if I go back to this example, What is the angle of the asymptote here? There is one pole, so n is 1, right? M is 0. So the angle of the asymptote is 180 divided by 1 minus 0, which is 180. Here is what? It's 180 divided by, you have two poles, 2 minus 0, so you see the angles are what? 90 and negative 90. And here is what? 180 divided by 3 minus 0, so the angles are what? 60 and negative 60. If you have 4, now you're going to go to what? Yes, 45 degree, and so on and so forth. So by changing the angles, you're forcing the asymptotes to bend to the right. You're bringing down their angles from bigger angles like 180 to 90 and then less than 90. And so when these asymptotes will go to the right, then the root locus will ultimately fall onto the asymptotes and then will move to the right-hand side of the imaginary axis. So this one can clearly tell you what's happening when you're adding to the poles. Now, what about the 0? Well, you kind of expect, right? If I add 0 and go back to that same formula, what happens? Well, if I make m bigger, then I'm making the whole n minus m smaller, assuming that n is always bigger than m. Then, since the numerator is smaller, the whole thing, the whole ratio will be bigger, and bigger angles means what? Means the asymptotes are moving to the left instead of the right. And that is a good thing, right? So let's look at this case here. So if you look at this bottom picture, case A, you have 3 poles, which is kind of similar to this case C on the top. Now you're going to add 1 0 here. And if you see, now the angles are changing. And they're changing from 60 to 90. If you see here, I'm going to 90. Not only that, if you see here, my root locus enters the right hand side. Here it doesn't. It only stays on the left hand side. And then when I move this 0 closer to the origin, okay, so I'm moving it a little closer, like here, what happens? The angle is still 90 degrees, but now what happens? The root locus shape changing, and instead of the dominant pole being very close to the imaginary axis, now they are getting further away, which is a good thing, right? Because we know that if I have a couple of poles here compared to here, the further away I move from the imaginary axis means this sigma, the real part, is a bigger negative term, so means the oscillations would damp faster. And now here I pushed it even further and closer, the 0 to the imaginary axis, and that moving 0 closer to the imaginary axis does the opposite on the whole root locus. It makes it even what? Further away from the imaginary axis. So now I'm getting more and more stable, right? We know that the more we move to the left, we are more stable. The more we move to the right, we are unstable. So adding a 0, which is like adding a derivative, and we discussed derivative in controllers. So adding derivatives means more stability, faster system, okay? So we have to keep in mind that these are the effect of zeros and poles, okay? Now, let's talk about the compensators that we wanted to discuss today. One is the lead compensator. That's the one that I'm going to discuss in this video lecture, and in the next that I'm going to upload immediately afterwards, I am going to talk about lag compensator. But what is a lead compensator? So lead compensator is a controller with a gain that you can adjust and a 0 and a pole. So it has 1 0, 1 pole, and a gain. And it has 3 parameters that you can choose. So it's not like a simple gain. It has 3 parameters that you can choose. One of them is this gain KC, the other one is this T, and the other one, very important, is this alpha, which is between 0 to 1. Now alpha, since it's between 0 to 1, it makes the pole overall a bigger thing compared to the numerator, right? Because alpha is in the denominator of this term, 1 over alpha t. And since alpha is like, let's say 0.5, so if the 0 is at negative 1 over t, the pole is at what? Let's, again, if we assume that alpha is 0.5, then the pole here is at what? Negative 2 over t, right? So you clearly see that the pole is a negative number with bigger magnitude, and so we say that the pole is further away from the imaginary axis, or 0 is what? Closer to the imaginary axis compared to the pole, right? Okay, so if I basically draw it in the draw the pole and 0 of that in the complex plane, the pole is further away here and the 0 is closer to the imaginary axis. Okay, this is a lead compensator. And in this course, we put the lead compensator always in series with our plant. So we do not put it back in feedback, or we do not put it in parallel. We always put it in a series configuration. Now, what is really a lead compensator? So the lead compensator, we're going to see this frequency plots later. These plots that you can see in this slide are called Bode plots, and we're going to see them in the next chapter. But if I just look at a lead compensator in the frequency domain, again, we're going to see it in more detail. But if you look here, there are two plots that you can see. The top plot is called the magnitude. The bottom plot is called the phase of a lead compensator. If you see here, the magnitude of this lead compensator is a negative, small negative numbers, means this is the logarithm of magnitude, okay? So you see it's in decibels. So this vertical axis here is actually 20 times logarithm of magnitude of the filter or the compensator. So when it's big negative, like negative 20, means that magnitude was what? Because this is log 10, of course. That one like was 0.1, right? Because log of 0.1 in the base of 10 is negative 1, and multiplied by 20, you're going to get negative 20. Okay? So small magnitudes at lower frequencies. This is lower frequency, right? And these are higher frequencies. So in lower frequencies, you have a small magnitude. In higher frequencies, you have bigger magnitude. Yeah, what is that? Have you ever seen that in any of your courses? Yes. What kind of filter, what kind of a device is that allows basically the high frequencies to pass without too much mitigation in their magnitude, but it's gonna bring down the magnitude of what? Low pass frequencies. So this filter, this device, this lead compensator, does not like low frequencies. It bring their magnitude down, damp them out, but high frequencies say, yeah, you're welcome, just go pass. So what kind of filter is that? Yes, it is called a high pass filter. Okay, so a lead compensator is a high pass filter, and exactly opposite of that, you're going to see later, the lag compensator is a low pass filter. It has high magnitudes for low frequencies and small magnitudes for high frequencies. Okay, so it damp out high frequencies, so it's a low pass filter. So this guy is a high pass filter. If you wanted to relate it to the real world, it is actually a high pass filter. And the thing that we'll look here in this course from it is this guy here, phase contribution. Okay, so we'll talk about this. The main thing that this compensator does for us is a phase contribution, phi, that we are going to get from this filter or this compensator. So now going back, as I said, there are three parameters, K, C, T, and alpha, that we are going to find to provide these requirements, right? And in order to do that, we have to go through a process. So this process has 4 steps, 1, 2, 3, 4, and I'm gonna through them one by one. But to do that, I'm gonna use an example here, which is also in your textbook. So while we go through these steps, I'll try to use this example in your textbook and go through and explain it step by step so that you can relate to these procedures from 1 to 4, okay? And I explain everything. So what is this example that we are going to work? So the example is this. I have a system here, an original system, 10 over s times s plus 1. And this system has dominant closed loop poles at negative 0.5 plus minus 3.1225 I, which will give me a very low damping ratio of 0.15 or 0.16. And means low damping ratio means what? Large overshoots, right? I don't like it. I don't want this system to show big overshoots. So you add a lead compensator to bring down the damping ratio to a bigger number, so bringing down the overshoot, and also do not use the small omega n, make the omega n bigger so that the settling time is also good, right? See if you can do it. So let's talk about several things together here to refresh our minds about what we had in the past. First, it says the closed loop poles of the system are at these locations. How did they get this? Using the system that we have. So I'm going to review everything for you so that hopefully this time that you are off classroom and not face-to-face, it helps you review the material through these examples that I go through. And that's why my lectures are getting a little longer than a typical class, but I would rather explain everything. So the G here is, the G here is 10 over s times s plus 1, and h is simply 1, right? There is no transfer function in the feedback. And if somebody says, okay, where are the closed loop poles? Of course, first we say the closed loop transfer function. In this case, there is no symbol for them, or there is C and R. So C over R from here is going to be what? It is going to be G over 1 plus GH. And if we plug in this, so 10 over s times s squared, s times s plus 1 over 1 plus 1 times the same thing. And if I make this smaller for you and simplify it, it's going to be 10 over s squared plus s plus 10. Okay, so this is the closed loop transfer function, right? And this is in the standard form. This term here is omega n squared, if you remember, and this term here, this 1, which I don't have, this 1, let me use a different color for you. So this 1 that is missing, this 1 is what? That is 2 zeta omega n, if you remember them. So if you write them, omega n squared is 10, therefore omega n is square root 10, which is 3.1, right? Square root 10 is 3.16. And since 2 zeta omega n is equal to 1, therefore your zeta is 1 over 2 omega n, correct? So 1 over 2 means 0.5. So 0.5 divided by this omega n answer, you see that it's 0.1581. Okay, and I just write it 0.158. Let's use 3 decimals to go standard. So 3162, 158. 62 and 158. So we know that damping ratio is a number between what and what? Yeah, the magnitude of the damping ratio is less than 1 in general, right? And the bigger it is, the the more damping I have in the system and the less overshoot, right? So what is the overshoot here? If I calculate the maximum overshoot, if you still remember the formula, it was E to the negative pi zeta divided by square root 1 minus zeta squared, right? And if I calculate this number, so let's do that. So exponential of negative pi times zeta divided by square root of 1 minus zeta squared, right? The whole thing exponential, 0.605. Which translates to what? 60.5%, right? If it's a unit step function, instead of going to 1, it goes to 1.605 in the first peak. So I have 60% overshoot, which is quite high. That's a big overshoot. I don't want to go 60% above a step function. I just want to go a little bit above. So the system now says, well, I don't want that. I want you to go to what? A zeta equal to 0.5. 0.5 translates to how much of overshoot? If you recalculate this MP, but using 0.5 instead, okay, so here I'm going to do it using 0.5 for you. You see that it's only 16%. So I want to go from 60% to 16% overshoot, and at the same time I want my omega n not to be changed significantly. If you go back and look here at the example, it says keep omega n at 3, right? So my omega n was how much? 3.16. It says do not change it significantly. I don't want you to change this. Do you know why? Because the settling time, if you remember, TS was what? 4 or 5, depending on the criteria used. If you use 5%, it was 4 over what? Sigma, and sigma was zeta omega n. So if I make omega n smaller, it makes the settling time bigger, and that's not a good idea. So if we want our settling time to get smaller, which means the system settles on the final value faster, what you need is the denominator to be as big as possible. And to make denominator bigger, we need what? Both zeta and omega n to be bigger. Now, we did not make omega n much bigger, but by increasing zeta, not only I'm bringing down the overshoot, also I am helping with the settling time. Okay, so now the question is, this is the root locus of the original system, 10 over s times s plus 1. You clearly see this system does not have a 0. It has 2 poles and 0 and negative 1, which you can see here and here. The angle of the asymptotes, if you calculate it, is 180 divided by 2 minus 0, so it's 90 degrees, which you can see here. And this is the root locus of the system. Now, is the system capable of giving me such zeta and such omega if I just change k? So here at these 2 poles, if I go back, at these 2 poles, what is the gain? So the gain at these 2 initial poles is what? 0. And as I move along it, k goes to what? To infinity. Is there any k desirable that can give me these 2 numbers? The answer is no. Why? Because if I draw the root locus or the loci for constant zeta and constant omega n, both of these, the place that they intersect is not on this root locus. How come? Well, if you remember, what was the root locus of constant omega? Yes, circles centered at origin with the radius equal to omega n. So the root locus for omega n equal 3 is what? It's a circle with radius of 3 units, like this. That's the root locus of omega n equal 3. What is the locus of the, not root locus, locus. What is the locus of zeta equal 0.5? If you remember, zeta fixed number was what? Was a line with what angle? The angle was arc cosine of zeta, and arc cosine of 0.5 is what? 60 degrees. So the locus for zeta of 0.5 is what? A line like this or like this, where this angle is what? 60 degrees, right? So these two guys are zeta equal 0.5, both of them, this one and this one. So now if you see, the place that these two desired loci are intersecting is here, right? Or here, both of them actually, because I have two dominant poles. Now, complex conjugate. Now, by moving along this initial original locus, can I ever get to these points? Absolutely not. So here you see a simple gain adjustment from any number between 0 to infinity for k is not going to make the system pass through the points I want. So I have to reshape this system. I have to reshape this root locus, and the way that I do it, I add a lead compensator, okay? So what I do is I say, well, this is my original system. Over s times s plus 1. Now I add a lead compensator behind it, which has a form of what? Kc times s plus 1t divided by s plus 1 over alpha times t. And by adding this lead compensator, I force the root locus that was like this originally, I forced it to now be reshaped such that it passes through those two interesting points, right? How can I do that? So the procedure is 4 steps. First, determine the location of dominant new poles. Where are they? So in order to do that, I redraw that root locus I just drew for you, but I do it here. So if these are the real and imaginary axes, like this, the root locus for constant omega was what? Was a circle centered at origin, right? And then for constant zeta, it was a line. So I have to draw a line like this, and then another one like that. Correct? They have the same angle. So this one has a radius of 3, and this one has an angle of 60 degrees. So I'm looking for these 2 points. Where are they? Well, I don't think that's so hard because this radius is 3, this angle is 60 degrees. So if I calculate the location, clearly if I call this x and if I call this y, clearly x is what? 3 cosine 60, which is 1.5. Of course, with if I include the sine. So if I include the sine for you, it is going to be negative 3 times that, so it is going to be negative 1.5, and then y is going to be what? Oh, y is going to be, of course, 3 times sine of 60, which is 3 square, 1/2 is square root 3, right? So 3 times sine of 60, which is 2.598. So this is the location of the dominant poles, negative 1.5 plus and minus 2.598 times I. So I have to move my root locus such that it passes through these 2 new points. Good, so that's step number 1. What is step number 2? Step number 2 says, draw the root locus of the original system. Make sure the gain adjustment does not pass the root locus through the desired points. We just checked it, it's not going to happen. If it doesn't, then calculate the angle deficiency of the original system for the new poles, and that is the angle that the lead compensator has to contribute to force the new system pass through these new poles. Okay? Now, if this angle is too large, like if you go back and look at this picture, so what is the angle? You see that the lead angle that I have, the contribution phi m for a typical one here, is showing something like, I maximize this for you. You look at this angle, it's around like 60 degrees or so. So somewhere between 0 to 90 is a typical, but if you found like I need 150 degrees or so, maybe instead of using one of them, use a cascaded, okay? So you might add one here and then one here. Okay, so you might add a GC1 here and then a GC2 here. Once you basically cascade them, the angle contributions will be added together. So if it's typically more than somewhere between 60 to 90 degrees, especially more than 90 degrees, you might consider 2 of them. But okay, so the important thing here is this term, angle deficiency. What is it and how do we calculate it? It says it is equal to 180 minus sum of the angles from original closed loop poles to the new pole plus sum of the angles from original closed loop zeros to this new pole. Okay, so if I go back and look at this root locus, so here I'm gonna draw the root locus for you again here. So this is, these are the x's. The root locus of that system, if you remember, is something like this. Let me use a bigger pen. Like that. And so I have one pole here, I have one pole here. This is at 0, this is at -1. I go somewhere in between these, and then what? One goes up like that. One goes down like this. Gosh, it is really hard to draw with pen on the laptop. At least it's not for me. So these are the original poles, although I don't need the whole root locus, but this is the original root locus. And then the new pole is here. If you remember, it's somewhere like here. This is the new pole, where this guy is -1.5, and this guy was 2 point, how much? 598. So it says the angle deficiency phi is equal to 180 minus sum of the angles from zeros of the original transfer function to this pole. Now the original system does not have any zero, so we are not going to add it to anything, but we subtract it from the angles of what? The original poles to the new pole. Okay, so you can see it here. I made it bold font for you. So 180 minus sum of the angles from original poles to the new pole plus sum of the angles from original zeros to the new pole. Again, this system does not have original zeros, right? All we have is two poles here. There is no zero over there. So we have only pole at s equals 0 and s equals 1. So what I need is to connect these original poles to this new pole like this and like that, and then measure the angles and subtract them from 180. So one of the angles is this one. If I call it like phi 1 or theta 1, whatever you want to call it, and the other angle is this one here. If I call that phi 2, so it is 180 plus nothing because there is no zero minus summation of these two angles, phi 1 and phi 2. That is the angle deficiency. And how much is phi 1 and phi 2? So we know this angle here, this angle was how much, if you remember? That was 60 degrees, right? Correct? So how much is phi 1? Clearly from this picture, phi 1 is 120, right? So that's not hard to get. Phi 2, you need to do a little bit of trigonometry, okay? Because you have 1, you have negative 1.5, and then you have what? 2.59. So instead of phi 2, I'm going to find this complement of phi 2, this angle here, whatever you want to call it. Let me call it phi 3 if you don't mind. So what is phi 3? So phi 3 is tangent inverse of, if you look at this triangle here, this one, what is it? The side in front of it is 2.598, and the adjacent side is between what and what? Between negative 1 and negative 1.5, so it's just 0.5. Correct? So that's phi 3 that I calculate, and then phi 2, the angle that I'm interested is 180 minus phi 3. So if I use MATLAB and calculate the angles, the angle of interest for me is going to be 100.89. 100.89 degrees. And phi 1 is 120, so it's not too hard to calculate. And now if I plug them into the formula for pi, the angle here is going to be 180 minus 120 minus 100, so there's going to be negative 40.89. So this is the absolute value of that. You see, instead of the angle being 180, the angle is less than 180. It's negative. These two angles are more than 180. So I have to bring this lead compensator to contribute an angle of 40 degrees for me, a positive 40 degrees. Right? So I want this angle to be I want that angle to be 40.89 degrees, and that positive will be added to these negatives and make the whole thing back to what? 180 degrees. And you might wonder, where is this 180 coming from? Anybody remembers? Yes, that is from the Root Locus condition, right? If I go back and look at the initial thing, there are two important conditions for Root Locus. What are these? The magnitude at a pole should be 1, and then what? the angle at the pole should be a multiple of 180, right? Any odd integer of 180, if I plug in 0 here, you're going to see the angle should be what? 180 or negative 180, which is the same thing. So that 180 is because that's the condition, the phase condition for a Root Locus in general. If this pole has to be on the new Root Locus, the angle at this new pole, the angle of the total system, which is GC times G, the angle of the new open loop transfer function, right? The new transfer function for me is now what? If this is G and this is GC, the new open loop transfer function is GC times G, H is 1. So the angle of this whole thing at this new location should be what? 180. But right now, these two guys, the angle that these two have is more than that, right? The angle that these two guys have together, sum of them is 200 something, right? If you add them, you see the angle is 220. But I just needed 180, so the difference is 40 degrees that this lead compensator has to bring in and contribute, okay? Good. So now that I know that my lead compensator has to bring in 40-degree angle and contribute, what do I do next? So the next stage is, now this one can tell me how to determine two of the three parameters, alpha and t, okay? Now, the problem suggests that you can do it by calculating a bunch of numbers, or you can do it graphically. I'll show you the graphic method of calculating the t and alpha, which is a little bit easier to grasp, but if you have choice, which you typically have, to choose between t and alpha, then try to choose alpha as big as possible. And the reason is, if you look at the static velocity constant, error constant, kV, for the new system, which in general is the limit of S times open loop transfer function, which is in this case GC times G, if you do that, multiply S by the system and calculate it, then kV, as you can see, depends on what? Depends on parameter alpha and the limit of SGS. So it does depend on alpha, and it's linear proportional. So if I make alpha 2 times bigger, it makes what? kV 2 times bigger. And what's good about that? We know the bigger the kV, the smaller the steady state error. So let me show you this very fast, and then we go and talk about how to determine alpha and t. So first thing is, 1 second, let me see if I'm still recording myself. Ideally I should, but just want to make sure that I'm still recording. Okay, so as you can see here, when S goes to 0, the limit of the lead controller as S goes to 0 is Kc times alpha, and that is clear from the definition of it, from the formula. You can see here, as S goes to 0, you're going to get Kc times 1 over T divided by 1 over alpha T. If you simplify the T terms, you're going to get Kc times alpha. So clearly bigger alpha here means bigger kV, and if you remember, the error, steady state error in response to a unit ramp function was 1 over K times V. So the bigger the kV or alpha, of course, the smaller the steady state error, which is desired. Now, as we just saw, the angle contribution for this lead compensator in this example is about 40 degrees. And using that, we should determine alpha and T In other words, since alpha and t would determine the location of 0 and pole of the compensator, what we want to do right now is to determine where the pole and 0 of these compensator are located. And if you remember, I told you that there are some computational ways and there is a graphic way, and what I would like to do here is go through the graphic way, which is quite easy to understand. So what you do is, here point P in this picture is the new location of the pole, which, if you remember, was negative 1.5 plus 2.589 times I. This is one of them. And so if we call that point P and origin O, what we do here is, and the instruction is written here, what we do, we draw a horizontal line passing through P to the left, and we call this line PA. We also connect P to the origin, PO. And then we basically bisect the angle APO using line PB. So the angle APO is now divided into two equal parts. One is APB and the other one is BPO. Okay, so this angle and this angle are the same. So then what we do is, the angle phi that we had, we consider half of it to the left of line PB and half of it to the right of line PB, and we form the lines PC and PD. Okay, so once we get line PB, then we form lines PC and PD using half of angle phi, the contribution angle, and wherever line PC cuts the negative real axis, that is going to be the location of the pole. Wherever the line PD cuts the negative real axis, that would be the location of the 0. Okay, so negative 1 over t and negative 1 over alpha t, the 0 and pole of this compensator. And so that should give us t and alpha. Now, if we refer to this example, let's do it on the paper, because although this looks quite easy and graphical, but when you really want to calculate the accurate location of C and D, we have to do a little bit again of tricks. So what I would do here is, I go back and I would redraw that picture you just saw over here. So this is one axis, this is the other one, and what we had was, we had point P here, and we connected P to the origin O. We drew a horizontal line A. Then we divided this angle APO into two parts like this, and we call this line PB. And then the angle phi, we used half of it to the left side of this, or we go like clockwise. And then we go also the same angle phi over 2 counterclockwise, and PC and PD, and this is the location of the 0, negative 1 over t, and this is the location of the pole, negative 1 over t times alpha, and this angle was phi over 2, and this angle was phi over 2. Okay, so this is the picture we had. Now, using the information that we had, we have to find exactly the location of these points. So if you remember the location of the new pole here, if we go back and look, it was 2.598, okay? So this point was 2.598, and the x of that point, if I can write somewhere, was 1.5, or negative 1.5 actually. And phi, angle phi, was more than 40 degrees, right? 4089. So angle phi is 4089. That's the angle that we have. We'll look at the absolute value of that. Now, using that, if I call this point, let's call this point, let's call this just whatever you want. Let's call it point maybe F, and let's call this point G maybe, and this point H. So the goal is, given the location of P and the angle phi, can we find the coordinates for points F, G, and H? Let me make sure this G is readable. So that point is G and this point is H. Okay, so if I ask you what is G, okay, what would you say? So first, what is the angle OP? What is between OP and the x-axis? If you remember this angle, was how much? 60 degrees, right? That was for zeta of half. So I know that angle 60 degrees. And so therefore, each one of these angles also is 60 degrees, right? Because this is 60, and then those two angles that are equal, this one and this one, these two that are equal, they should also be 60 and 60. Okay, so every angle here is 60. Okay, now using that, can I get anything? So what I can do for you here is I draw these triangles for you here. So I have three triangles between FGP, GHP, and HOP, right? Let me redraw them for you here. So I have one line like that, then I have one line like this, then I had a line like that, then one like this, and one like that. Okay, and this was P, this was O, this was F, G, and H. And I know some angles, right? I know the angle between GP and GF and GP and GH. So I know these two angles. These are both phi over 2, which I know exactly. I also know this angle is 60 degrees. I know the length from OP. I exactly can calculate that, right? How much was it? Yes, that was equal to omega n desired. So the length OP was 3, if you remember, the radius of that circle. So that is 3, and I also exactly know how high P is and what is the horizontal position of P with respect to O. So I know everything. Now, can I find any other length? The length of interest for me is O to H and O to F. These are the things that I care about, right? O to H and O to F, the location of pole and 0, because this guy is the 0, right? And this guy is the pole. So if I can find them, then that's all I need. But right now, let's see what I have. So if you look at the angles, considering the fact that I know this angle, let's focus on this one. How big is this angle? And let's see if we can find it. I guess we can, because if you look here, the angle between GP, right, and PO is 60 degrees. So this whole thing, this one from here to here, this whole thing is 60 degrees. So this angle is going to be 60 minus phi over 2. Right? So I have that angle. And now, if I look at triangle OPH, I have all angles. So this one is 60 minus 5/2, that is 60. And this one, of course, I can find. It's 180 minus sum of the two, right? And then, so if I want this angle, that's what? That's 60 plus 5/2. Right, so sum of this one, and this guy is 60. Sum of this one, and this one should be 180, which it is. And I have one side. Can I find the other two sides? Yes, I can. So if you know the laws of sine and cosine, those would help us. So the law of sine says what? The law of sine says each side divided by sine of angle in front of it, that ratio is the same for all three angles. In other words, length OP divided by sine of angle in front of OP in that triangle, which is the angle 60 plus 5/2. This is equal to a similar ratio for pH, which, by the way, I don't care, so I don't, let's see, do I need to care about pH? For the moment, let's just focus on OH. If I just focus on OH, it's going to be OH divided by sine of 60 minus 5/2. And since I have phi and I have OP to be 3, from here I can easily find OH, right? Because everything is known. And if I calculate OH, the value for it is going to turn out to be, I have the number negative 1.94. And since we're going to use 3 decimals, so I have a 3 as well, 9.43. So that is the location of the 0, negative 1.943. Of course, here we're just going to get the absolute value of it. So it's just the magnitude of it from here. But that's the location of the 0. Now, what about the location of the pole F? So what I can do, this time I look at the big triangle, OPF. If I look at OPF and apply the law of sine again, I can say OP divided by sine of this angle, if I can find it, is equal to OF divided by sine of the top angle. And what is the top angle? What is the other angle? So this whole angle here, which is in front of OF, this whole angle is, of course, what? It's 60 plus 5/2. The whole top angle. Right? Because this portion of it is 60 and that portion of it is 5/2. So 60 plus 5/2. And again, since this is 60, that is 60 5/2. So this guy is going to be 60 minus 5/2. So this is going to be 60 minus 5/2. And from here, again, I can find OF because everything else is known. And if I do that, I'm going to get 4.646. So that is the location of the pole. So I could find both locations using the law of sine or sines. Now that I know this, what is the location of the 0 of a lead compensator? If you go back and look at the formula, the location of 0 is what? Negative 1/t when the numerator goes to 0. And where is the pole? Negative 1/alpha t, right? So if I go back, this number here is This number here is 1 over t. From here I can find t. And the number for t is going to be, of course, reciprocal of that. So 1 divided by 1.943, which is 0.515. And then since this guy is equal to 1 over alpha t, and since I have t, from here I can have alpha. And from here, if I solve for alpha, I'm going to get 0.418. Okay, and this is right. As you can see, this is less than 1 and bigger than 0. So if you ever, by any chance, you come here and find a number bigger than 1, then there is some calculation error somewhere. So there we go. I found alpha and t, and this alpha is probably the biggest alpha per method that I could find. Good. So now that I got my alpha and t, now the last part is to find the remaining gain Kc. And it says it comes from the requirement of the open loop gain. So if you remember again, at a desired closed loop pole, what should I have? Two conditions: the phase condition, from which I got the contribution angle, and the magnitude condition. The magnitude condition says what? It says the magnitude of the open loop transfer function at the desired location should be 1, right? So if I go back here and look at this example, in this example, what was my open loop transfer function? GC times G. The magnitude of this at this new pole should be 1. So if I go here, the magnitude of GGC at the location S was what? Negative 1.5 plus 2.5, was it 89 or 98? 98. 298i, this should be 1, right? Remember, that was the magnitude condition. And what was G? What was GC? So GC in my case is again Kc, that I don't know, times S plus T, 1 over T, of course, divided by S plus 1 over alpha T. And since I have T and alpha, this is going to be Kc times S plus 1.943 divided by S plus 4646. So 4.646. This is GC. And what was G? Yes, G, if you remember, was 10 divided by S times S plus 1. So what I do, I plug in this complex number into G and into GC, and it gives me a big complex number with Kc as just a scalar in it. And then I set the magnitude of that to be equal to 1, right? Or in other words, if I just factor out GC and find the magnitude of this term at the location and magnitude of this one at the location, so this magnitude times that one times Kc should be equal to what? To 1. So if I know these two magnitudes and divide 1 by those two numbers, multiply together, I can find what? I can find Kc, and I assume at this point you all know how to calculate magnitude of complex numbers. So if you do it, then you're going to get 1.229. Okay? So that is your lead compensator. 1.229 times S plus 1.943 divided by S plus 4.64. You see it has 1, 0. It has a pole. The pole is further away from the imaginary axis. And now you might say, okay, I have done all of that, right? What was the desired things that I had? That zeta is equal to 0.5 and omega n equals 3. How about we look at the root locus of the original system versus the root locus of the new system and confirm whether this newly added thing to the system, this newly added lead compensator, when combined in series with G, would give me what I really needed. And I say, absolutely, why not? So we first say our locus of, if you remember, the numerator was 10 and the denominator was s times s plus 1. So this is the original system, which we have seen, the two vertical lines separated at half. So that's exactly what we had. Now, instead, what I have this time is G times GC. So my new open loop transfer function this time is GC times G, which is, if I put all of those numbers together, so I have 10 times this number, so 1229, right, times S plus, the 0 was 1943, and then divided by S times S plus 1 times S plus 4.646, right? So this is now my new open loop transfer function that I'm going to use to draw the root locus. So let me move it to the side and I do it again. So this time, this is going to be 10 times that, so it's going to be 12.129 is the coefficient of S, and then 12.29 times 1.943. These are the coefficients of numerator, and then denominator, which is this guy, is now multiplied, so I use the conv command, by a new term. And the new term is a linear with 1 and 4.646, okay? So now let's look at this one. So now this is the new root locus, and I want to add the constant locus of zeta 0.5 and omega n3 to it so that we see if they intersect or not. So I use the command sgrid, if you still remember, and I pass to it a range for zeta, and the range I want for zeta is maybe only 0.5, and the range I have for omega n, let's say maybe just 3. Let's see what happens. Okay, and now you see they are added to it. Of course, again, the aspect ratio here is not 1:1. You see here is 6 units, that is 20 units. So that's why instead of a circle, it looks like an ellipse, but that's not the case. So now if you see here, if I can zoom somewhere for you around this region, so you see that, there we go. This line and the circle and the root locus, they are all intersecting at this point, right? And what is it? My zeta is at negative 1.5, which we found. And this one here, let's just look at that point if we can. Can we just click somewhere close? Oh, yeah, the reason is this is still on Zoom. Can I now click somewhere? Okay, let me put it back to the actual size. You know what, let me do it one more time. Let me see if I can use x as equal for this command, not n equal. There we go. Now it is really what I need. And I should be able to click somewhere like that and then drag it very close to where I want. So as you can see here, it's very close. And damping is what? 0.5, and frequency is what? 3, and the location of the pole is negative 1.5 and what? 2.63, which is, I guess, what we found, right? Or close to what we found, because yeah, it was 2.6 and negative 1.5, which is the same thing as here. Damping is almost 0.5, omega n is almost 3, and the overshoot is 16%. Remember, that's what we calculated, I assume, somewhere. Where was that? I showed you that or it was in the PowerPoint, I guess, somewhere here, that I calculated for you that the overshoot is going to be 16%, which is good. I said it goes from 60 to 16. So you see it is happening, and the magnitude of the gain of the system is 1, of course, because I already considered the gain in Kc. So everything looks perfectly fine. Okay, and now if we compare the responses of these two systems against step function. So first I pass the step to the first system. This is the step of the first system, right? Oh, yeah, you have to feedback it first. Yeah, when you pass the step, you cannot pass the open loop, you have to pass closed loop. So system 1 was, let me do it this way. Sys11 was transfer function of this. So this was the open loop, but the actual system 1 was feedback of sys11 and h, which was 1. So that is the actual transfer function of the closed loop system in before we added the compensator. And this is the actual step response of that system. You clearly see instead of 1, it goes to 1.6, so it has 60% overshoot, and it's quite slow, almost like after 12, 13, 14 seconds, it kind of settles down. Now I add a new system, where the new system is this one. So I call this sys22. It's a temporary system. Is transfer function of this, and then I say system22, give it the unity feedback, and call it system2. And now I want to plot the step response of system2 in a separate figure, which is this guy. So now if you compare them side by side, clearly you can see that the improved system, the one on the right with the compensator, first of all, it is not showing a huge overshoot. So overshoot is much smaller compared to this one, and it is quite faster. In like 4 seconds or so, it is settling down. So that's what you see here, improved response using a lead compensator, right? And we can do all sorts of things later. For example, we had the system 11, right, which is, or 22, which is this one. And I'll show you later when we plot the frequency responses of these systems. One of the plots is this guy here, Bode plot. If we do that, this is the plot of course, you have to do it just not that. You have to define a different thing, and that is the compensator only, not with G included. So if you call this one to be the compensator, right? So just call it system compensator, this one. And if I do system compensator, there we go. You see the angle contribution here, and the high pass type of behavior.